One of the first things you notice about the stars when you go out to do observations is that they vary in brightness. Some stars are brighter than others. So, in this video, we're going to talk about how we think about it, how we measure the brightness of a star, and what it tells us, what the brightness level of the star tells us. So, first, let's just take a look at the image over here. Um, we've already talked a little bit about the color differences in stars, and now let's focus in on the brightness differences. So it looks like the brightest stars right here. Maybe these two over here are the brightest stars. But there's a variety of brightness within the stars. And so it might be tempting to look at this picture and say, well, these stars must be closer to us and the other stars are far away. The assumption being that stars are all naturally the same brightness level, and then how bright they appear to us changes with how far away they are. Well, that thinking is not completely incorrect. It is true that the farther away stars are going to be dimmer than the closer to us stars. But there's also variation in their intrinsic brightness, how much light they really are putting out. And so we need to distinguish between the apparent brightness of a star, which is how bright it appears to us, and their luminosity, which is how much light they're putting out, which is irrespective of distance. The luminosity does not change with how far away they are. And really, it's the luminosity and the distance that determines how bright a star will appear. Some stars will appear bright because they're close to us, and some stars because they're just really big, bright stars. Or it could be both. So let's think about how stars appear to us. The first way to discuss the brightness of stars is called the magnitude scale. And the magnitude scale is visually how bright you perceive the star. So it's sort of like you look up at the sky, you look at the stars, and you put a number on it. You put a magnitude number on it. And it works in reverse order to what you think. This is historical. This is the way it was originally designed. So the bigger the number, the dimmer the star is, and the lower the number, the brighter it is. And so if you're thinking about it that way, when it started out, like the brightest stars were around a 0 magnitude, the brightest stars in the sky, so not including the planets and the sun and the moon, the brightest stars in the sky were around a 0 magnitude. And then you'd have first magnitude, second magnitude, third magnitude stars. And the higher the number, the dimmer the star was, the fainter it was, the harder it was to see. Okay, so this is just perception. You're looking up at the stars, this is what you see. Well, it turns out that the amount of light coming off is related to the apparent magnitude. So that number that you'd put on it is related to the technical scientific brightness, like the energy output that you are receiving. However, it's not linear, so we don't perceive light linearly. Similarly, we don't perceive sound linearly either. In both cases, we perceive them logarithmically, which means something that we perceive as like one level louder or one level brighter is 5 times brighter or 2 times brighter or 10 times brighter. That's what we mean when there's a logarithmic scale to it. And that's the case with magnitude. Now, specifically with the magnitude scale for brightness, 5 magnitudes different means 100 times different in brightness. So if the number is 5 magnitudes smaller, then it's 100 times brighter. So the example I used here is Venus, which is around a -5, so it's close to -5. I'm fudging it a little bit there. But let's say it's about a -5 in apparent magnitude. Compare that to Alpha Centauri, which is a 0 in apparent magnitude. So that's 5 magnitudes lower. That means it's 100 times brighter. So let's say you're comparing everything to Alpha Centauri, which is a 0 on this magnitude scale. Then the stars over here would be 100 times brighter. These would be 100 times brighter than that, so 100 times 100, right? 10,000. and then 100 times brighter than that, and then 100 times brighter. So every tick mark on here, every 5 magnitude difference, you're talking about 100 times more energy that you're receiving from the star's light. That's how this magnitude scale works. And so just so you have some sense of the range of numbers, the sun is in between a minus 25 and a minus 30. That's by far the brightest thing that we see. The full moon is much less bright than the sun, which is why on full moon night it's not like day. It's brighter, noticeably brighter outside when it's a full moon, but it's not like daytime. And then if you go to the other end, what can we see? There's a limit right now with our telescopes to how much we can see. And with the Hubble and the Keck telescopes, which are our most powerful telescopes, we can see up to a magnitude of 30. With your unaided eye, so not using a telescope or binoculars or anything, you can see a little past a magnitude of 5. So all the stars that you see in the sky when you go up at night are in between, if you're including the planets in that, -5 and +5 about. So this range here, that's what you can see when you look up at night. Now there's some math that we can do with this that relates the brightness. So I keep saying brightness, what I mean is the energy that you're receiving from the star's light. We can relate that to the magnitudes. And because it's a logarithmic scale, we get a logarithmic equation. So here is the magnitude difference, call 1 star 1 and 1 star 2. So this is the magnitude difference, and this is the ratio of their brightnesses. Now, depending on the information you have, you might want to use the equation to find the magnitude difference, or you want to find the brightness ratio, how bright is one relative to the other. And in that case, you would use it this way, which is just inverting this equation, solving for B2 over B1. So you can use either equation depending on the context to figure out either the ratio of brightnesses or the magnitude difference. So let's take a look at one example of that. So looking back to the apparent magnitude plot, you'd see Alpha Centauri is a 0 and the full moon is a -12.5. So the magnitude difference, so let's say this is star 1 and this is star 2, the magnitude difference would be 0 minus -12.5. So the difference is 12.5. Then I can use that magnitude difference to find the brightness ratio by taking 2.5, raising it to the 12.5, and we'd find 94,423. What that means is that the full moon is 94,423 times brighter than Alpha Centauri. Its light put is 94,423 times the light output of Alpha Centauri that gets to us. Remember, we're still talking about apparent, so this is what it appears. The intrinsic brightnesses are very different. The moon is not nearly as bright as a star. But to us, because the moon is so much closer, it appears 94,000 times brighter than Alpha Centauri. Okay, now let's think about that luminosity. We've talked a little bit about this in the sun video. Last week we saw the sun has a luminosity of 3.8 times 10 to the 26 watts. So watts are the unit that we measure luminosity in. It's the light power of the star, so how much light energy is being output every second. And the numbers are really, really large. Light bulbs are measured in the same units. Light bulbs are 60 watts or 100 watts, while stars are 10 to the 25 watts or 10 to the 28 watts. They're just tremendously large light bulbs. Now we can compare its luminosity with its apparent magnitude. So on the apparent magnitude scale, we saw that it was between -25 and -30. More precisely, it's -26.74 on the apparent magnitude scale. And it's way brighter than anything else in the sky by appearances. But it's not the most luminous thing in the sky. So here it's important to focus on the terminology. Apparent brightness is what it appears to us. Luminosity is how much light power it actually has. And the sun is not the most luminous thing in the sky, even though it's the brightest to us. Just as one example, one of the bright stars in our sky is Sirius. I believe during the winter it's the brightest star in the sky, is 25 times greater in luminosity than the sun. So there are stars that are much, much more luminous than our sun. But its apparent magnitude is only minus 1.46. So it's a bright star compared to the rest of the stars, but nothing compared to the sun in apparent brightness. And the only difference here, or the difference here that causes the discrepancy is just distance. The sun is so much closer to us that it appears orders of magnitude brighter than Sirius, even though Sirius is 25 times more luminous. All right, so just putting it all together here, apparent brightness decreases with distance. So a star that appears dim with a high luminosity has to be far away. So if we knew the luminosity of a star, we knew it was a really, really luminous star, but we look up in the sky and it's not very bright, that tells us it's got to be very far away. On the other hand, if we see a bright, bright star and we know it has a low luminosity, it has to be close to us. So you might start asking the question now, well, how do we know the luminosity? The apparent brightness is sort of easy, you just look at it and see, but how do you know the luminosity? Well, sometimes there are alternative ways to figure out what the luminosity is, and we'll get into that in the coming weeks, some tricks that tell us what the luminosity of a star has to be. But also often, this works in reverse, that there's a way to determine the distance to a star, and that allows us to figure out its luminosity. So sometimes it works sort of in the backwards direction, where you can see how bright the star appears, and there's a method to determine how far away it is. So then, by comparing its apparent magnitude to its distance from us, we can estimate how luminous the star really is. So we'll sort of use this relationship both ways, either to find luminosity when we know the distance, or to find distance when we know the luminosity. And so that will be something that we come back to in the coming weeks as we learn about more different types of stars.